Okay, in this video we're going to be dealing with hypothesis testing. Okay, now the next 4 videos will be related to hypothesis testing for a proportion, also for a mean, and also for a population variance or standard deviation. Alright, now this first section, section 8-2, actually this deals with some of the basic concepts of hypothesis testing, and these basic concepts are going to be very important in the next 3 videos for this course. Okay, so let's begin with some definitions here. Alright, the first definition is just a hypothesis. When we're dealing with statistics, a hypothesis is nothing but a claim or a statement about a population parameter, well, about a property of a population. And again, that could be the population mean or the population proportion or the population standard deviation or variance. Okay, so pretty much a hypothesis is a claim or an educated guess about a property of a population. Now, what we'll be looking at is how to conduct a hypothesis test. And a hypothesis test is a procedure. So when we conduct a hypothesis test, we're doing a procedure for testing a claim about a population, a property of a population. Okay. So here we're just going to be applying a procedure for testing a claim about a property of a population. That's what we call a hypothesis test. And what I'm going to put up here is this handout, and this is also on Cruiser for those of you who are taking my class online. Okay, and it's under the additional documents section under course content. This whole thing represents the hypothesis testing procedure that we will be using, and it is 8 steps. Unfortunately, I can't fit all of this on the screen, but here you can see what those 8 steps are, and we'll go over each one of these one individually, and as we go along with these 8 steps, we'll be defining some terms as well and do some examples that are related to this hypothesis testing procedure. So in this case, of that first one, step number 1, you have to state the original claim in symbolic form. Then step number 2, you're going to state the opposite of the original claim. And then third, from steps 1 and 2, you're going to identify 2 things: the null hypothesis and the alternative hypothesis. So from steps 1, 2, and 3, I need to give you some more definitions. Okay, there are 2 types of hypotheses that you're going to have to identify. One of them is the null hypothesis. And the symbolic notation for that will be H sub 0. So the null hypothesis is H sub 0. And it is, by definition, a statement that the value of the population parameter is equal to, and let me underline this because that's going to be very important, some claimed value. So the null hypothesis is a statement that the value of that population parameter is equal to some claimed value. In other words, pretty much when we have a null hypothesis, we're always going to test the null directly, in a sense that we assume that it's going to be true, and we're going to reach a conclusion on whether or not to, whether to either reject the null hypothesis or fail to reject the null hypothesis. Okay? Now, in a null hypothesis, you're always going to have the equal sign, no matter what. The null hypothesis means that there's nothing has changed. There is no difference. Okay? So that means we always use the equal sign as the symbolic representation. It's going to be some population parameter equaling to some claimed value. That's why I underlined the phrase is equal to, because in the null hypothesis you always use equal to. Okay, now the other type of hypothesis is the alternative hypothesis. So next is the alternative hypothesis. Okay, and we denote that. Now for this class we're going to use H1. Some textbooks use H sub lowercase a. Some use H sub capital A. But for this class, we're only going to be using H1 for the alternative hypothesis. And that definition is this: it is a statement that the parameter has a value that somehow differs from the null hypothesis, and I'm going to abbreviate that as H sub 0. Okay? So I won't have to write out the word null hypothesis. I can just say H sub 0 is the null hypothesis. It's a statement that the parameter has a value that somehow differs from H sub 0, or the null hypothesis. And we use, for the symbolic form, we're going to use either less than, or greater than, or not equal to. Okay, only for the alternative hypothesis will you use one of those three inequality symbols, because that's a statement that does not have equality in it. Less than is strictly less than, it has no equality. Greater than is just strictly greater than, again, no equality. And of course, not equal to, it's just the opposite of equal to. Not equal to means no equality. Okay. So in this case here, let's look at how we can identify the null and alternative hypothesis, okay, from three statements which is given as a claim. So here is the first example. For the given claim, you want to complete parts A and B. In this case here, the claim is this: the mean weight of beauty pageant winners is 118 pounds. A study of 22 randomly selected beauty pageants resulted in a mean winner weight of 117 pounds. In this case here, part A, you want to express the original claim in symbolic form. Okay, so here's how we will approach this problem. So this is going to be part A. You want the original claim in symbolic notation. And by the way, I do have another handout that has some of the hypothesis testing common phrases for each particular inequality symbol. For less than, greater than or equal to, less than or equal to, and not equal to. Make sure that you print that off and refer to this as much as you need to. Okay? And this is also in the course content section of Campus Cruiser for those of you who are taking my online course. Okay? So now, in this case here, we're dealing with the claim that the mean beauty pageant winners is 18 pounds. Okay? So in this case here, we're dealing with the mean, so we use the Greek letter mu for the mean. And the word is represents the equal sign, 118. So the original claim in symbolic form is mu is equal to 118. Now part B is to identify the null and alternative hypothesis. Okay, now step 1 is finding the original claim. Step 2 is getting the opposite of the original claim. So here, the opposite of equal to has to be not equal to. So mu is not equal to 118. Okay, and from that we can get our null and alternative hypothesis. Now keep in mind the alternative hypothesis is that statement that does not have equality in it. So between these two, it's this one right here that does not have the equality in it. That's the mu is not equal to 18. So that's going to be your alternative hypothesis. The original claim with the equal sign is your null. So the mu is equal to 118. And usually I put this word claim next to mu is equal to 118 because that's the original claim. Okay, and later on you're going to be seeing why I put that there when we start going into doing this hypothesis testing procedure. So that's how you identify the null and the alternative hypothesis. Okay, here's another example. The claim is this: high school teachers have incomes with a standard deviation that is more than $20,500. A recent study of 148 high school teachers' income showed a standard deviation of 23,500. Now in this case here, part A, you want to express the original claim in symbolic form. Okay? Now the claim is this: high school teachers have incomes with a standard deviation. So we use the Greek letter sigma for your standard deviation. That is more than. The inequality for more than would be strictly greater than. And then 20,500. And by the way, I should say original claim. So that's your original claim here. Now part B, we want to identify the null and alternative hypothesis. So now we want the opposite of the original claim. Well, if it's not greater than, the opposite of greater than must be less than or equal to. Okay, so we got sigma is less than or equal to 20,500. And then from here we can identify the null and alternative hypothesis. Okay, in this case here, the null will always have the equal sign no matter what. Since this is a less than or equal to, that goes to the null, but it's still going to have the equal sign no matter what, because the null always has equality in it. So the sigma is equal to 20,500 for your null hypothesis. The original claim, where you got sigma is greater than 20,500. That's your alternative hypothesis. And in this case, the alternative hypothesis is your claim. Okay. And by the way, let me write off to the side which one of these inequalities are direct opposites of each other. If you have greater than, its opposite is less than or equal to. If you have less than, its opposite is greater than or equal to. If you have not equal to, its opposite is equal to. And this also is vice versa for each one of these. Okay? Okay, here's the third example where you have to write the null and the alternative hypothesis. The claim is this: at least 24% of internet users pay bills online. A recent survey of 368 internet users indicated that 28% 28% pay their bills online. So in part A, you want to express the original claim in symbolic form. Okay, now we're given a percent, so we have to use lowercase p for the proportion. And it says at least, so the inequality is this. And by the way, let me write the phrase original claim. So here the original claim is this. We use lowercase p because we're dealing with the percentage. At least 24%. At least will be greater than or equal to. And then 24% as a decimal will be 0.24. If you're given a percent, change it to a decimal by dropping the percent sign and dividing by 100. So the p is greater than or equal to 0.24. That's your original claim. Part B is identify the null and the alternative hypothesis. Okay, in this case here, your opposite, if it's not greater than or equal to, it must be less than. The opposite of greater than or equal to is less than. So P is less than 0.24. That's the opposite of the original claim. And from that, we can write our null and alternative hypothesis. So in this case here, the null always has equality. So in this case here, it's going to be P is equal to. And the null always has the equal sign no matter what. Regardless of whether you have greater than or equal to or less than or equal to, the null always has the equal sign in it. So P is equal to 0.24. And the opposite, which is P is less than 0.24, must be your alternative hypothesis. Because in the alternative hypothesis, it's either going to be a less than symbol or a greater than symbol or not equal to. Okay? So that's steps 1, 2, and 3. Writing the original claim, stating the opposite of the original claim, and then identifying the null and your alternative hypothesis. Okay? Okay, now back to our procedure. Look at step number 4. It says state the level of significance, which is your alpha level. So now we need to define what the level of significance is, or the significance level. The significance level is going to be the Greek letter alpha. That significance level is the probability of making the mistake of rejecting the null hypothesis, which is h sub 0, when it is true. Your significance level is going to be just that probability of making the mistake of rejecting the null hypothesis when it is actually true. Now, in the examples that you'll be doing, you will always be given a level of significance to use. And it'll state that in the problem. Now, the common choices are this. Alpha is equal to 0.05. Alpha is equal to 0.10. And alpha is equal to 0.01. Those are the 3 common choices for your significance level. And usually that's stated in the problem. So usually you don't have to come up with some type of alpha level yourself. But, you know, reality is, well, in these problems you'll see you'll be given the alpha level. Okay, step number 5. Okay. Now in step number 5, you're told to calculate the test statistic. Okay. Now there are 3 types of statistics that's going to be relevant to the test that you'll be using. Okay. Now for a proportion, which is of course lowercase p, this is what your test statistic is going to be. Z is equal to p hat minus p, that's divided by the square root of p times q over n. Now we'll go over each one of these individually, but I just want to, in later videos, but I just want to just introduce those 3 different test statistics to you. Okay. And then for the mean, now in the notes they have 2 formulas for the mean, but we're only going to use the one where sigma is unknown. Okay. And in this case, it's going to be t is equal to x bar minus mu divided by s over the square root of n. Okay, we're only going to be using that one and not the other one because it's rare that we want to find a calculated test statistic where the standard deviation for the population is already known. And then for the standard deviation, which is sigma, or the variance, and that's sigma squared. Its test statistic is this. It's a chi-square test statistic, and that's equal to n minus 1 times s squared. That whole thing is divided by sigma squared, or the square of the variance. Okay. Now we'll go into more details on those 3 different test statistics. Okay. Okay, and it would help to define what a test statistic is. That's going to be the value used in making a decision about the null hypothesis, or H sub 0. Okay, it's going to be a value that's used in making a decision about the null hypothesis, and we use that test statistic, and we find that test statistic by converting the sample statistic to a score with the assumption that the null hypothesis is going to be true. So we're going to be using one of these 3 formulas. That first one we're going to be using in the next video on proportion, and then on another video we'll be dealing with this test statistic for a mean where sigma is unknown, and then on another video we'll deal with the test statistic for a standard deviation or variance. Okay, so those 3 I'm just going to introduce to you. Okay, and also there are 3 types of hypothesis test. So let's look at the types of hypothesis test. Okay. The first one, and there are 3 of them, the first one is a two-tailed test. Okay. And in a two-tailed test, you're going to have something what they call a critical region, which I'm going to shade in red. Okay, so this shaded area is called the critical region, and this shaded area is the critical region. In a two-tailed test, that means that the area is in the two extreme regions, or what they call tails, under the curve. Okay, so here in a two-tailed test, the alpha level, which is your level of significance, is divided in two tails equally. Okay. And in a two-tailed test, your null hypothesis always has the equal sign, but your alternative has the not equal to symbol. So with the null hypothesis, if it's not equal to, it's a two-tailed test. So that means that the alpha level is split in two tails. Okay. Now, what that means is just this. If that test statistic is in either one of those critical regions shaded in red, you reject the null hypothesis. So these are the areas where you will reject the null here, or reject the null here. But if your test statistic is in between the two, you're going to fail to reject the null. Okay, so that's what a two-tailed test looks like. Okay, the second type is a left-tailed test. So number 2, we have a left-tailed test. And in the left-tailed test, the alpha level is in the left tail. Your entire alpha level is going to be in the left tail. So if I draw my normal curve, it looks like this. In this case here, the entire alpha level will be in the left tail. Okay, that's that shaded area. Okay. So in this case here, if that test statistic is in that shaded area, you're going to reject the null. If it's on this side, that's where you fail to reject the null. Okay. And in the null and alternative hypothesis, the null always has the equal sign, but your alternative will have less than. Okay. So if the alternative hypothesis has a less than symbol, then it's a left-tailed test. Less than means you have a left-tailed test. That means that the area is shaded to the left. And that's easy because this inequality symbol is pointing to the left. So that means we're going to shade the tail on the left. And then the third type is the right tail test. And in the right tail test, the alpha level is in the right tail. Okay, and I did forget to say alpha is in the left tail for the left tail test. But for the right tail test, your alpha level is in the right tail. So in this case here, here's the normal curve. The shaded area in red is your alpha level. Okay. So that shaded area is your alpha level. Okay. So if the test statistic is in this shaded area, that's the part you reject the null. And all of this on the left, you're going to fail to reject the null. Okay. And in the null and alternative, again, the null has your equal sign. The alternative this time has the greater than symbol. And in this case, your greater than symbol is that inequality symbol that points to the right. So that means you have to shade the tail on the right. Okay. So those are the three types of hypothesis tests. You could have either a two-tail test, or a left-tail test, or a right-tail test. And how would you know that you have a left-tail or a right-tail test or a two-tail test? You always look at the alternative hypothesis. Okay? So the hint is this. Your alternative hypothesis, which is H sub 1, determines the type of test you will have. So you always look at the alternative hypothesis to determine whether you're going to have a two-tail test or a left-tail test or a right-tail test. So again, if the alternative says not equal to, it's a two-tail test. If the alternative says less than, then it's a left-tail test. If the alternative hypothesis says greater than, then it's a right-tail test. Okay, so that's very important to determine the type of test that you're going to have. Okay. Okay, now going back to my hypothesis testing procedure, step number 6 says this. You're going to use either two methods, the p-value method or the traditional method, to decide whether to reject the null or fail to reject the null. Okay? So there are two methods that we're going to look at, which is in relationship to step 6 on the hypothesis testing procedure. One method is the p-value method. And let's define what a p-value is. Sometimes it's called the probability value. Because that's basically what it is, the probability of getting a value of the test statistic that is at least as extreme as the one representing the sample data. And that's assuming that your null hypothesis is true. Okay? It's a probability of getting a value of that test statistic that is at least as extreme as the one representing the sample data, and that's assuming that the null hypothesis is true. Okay? Now, in this case, I'm going to go ahead and bring this up here. Now, this is just a procedure. If you have a left tail test, if that shaded area, or what they call the critical region, is a left tail test, then your p-value is going to be the area to the left of that test statistic. That's for a left tail test. It's the area to the left of that test statistic. For the right tail test, then your p-value is going to be the area to the right of your test statistic. And if you have a two-tailed test, your p-value is going to be 2 times the area in the tail beyond the test statistic. And the reason for that is this: the alpha level is split in half. So what you'll be getting is 1/2 of a probability value. You want the entire p-value, so you have to get twice the area in that tail beyond the test statistic. Okay, so that's the only one that's going to be probably the confusing one, where you have a two-tailed test. You have to make sure that when you get your p-value, you have to get twice the area in the tail beyond the test statistic. Okay. Alright, now let's look at some examples of how to calculate a test statistic and find p-values. Okay. So this example deals with finding the value of the test statistic, and then the next few examples we'll look at finding the p-value. Here it says that the claim is that the proportion of peas with yellow pods is equal to 0.25 or 25%. The sample statistics from one experiment includes 50 peas with 143 of them having yellow pods. Find the value of the test statistic. Okay, so in this case here, our lowercase p is 0.25. And then the sample statistics from one experiment include 550 peas, that's your n, with 143 of them having yellow pods. So x, that's the number of successes, that's 143. Which means, to find p hat, we take x and divide that by n. X is the number of successes, n is the sample size. So p hat will be 143 divided by 550. And if you do this on the calculator, you'll get 0.26. 143 divided by 550, 0.26. Well, if p hat is 0.26, well, we don't need q hat. Well, we know p is 0.25, but we need to find out what q is. That's 1 minus p, or 1 minus 0.25, which is 0.75. Okay, for this one, to find the value of this test statistic, we're dealing with a proportion, so that means we have to use this formula. Z is equal to p hat minus p divided by the square root of pq over n. So in this case here, your p hat was 0.26 minus p, which is 0.25. All that's divided by the square root of. Your p is again 0.25 times q, that's 0.75, divided by n, which is 550. Okay, now the way we do this in the calculator, it'll be best to put the numerator in parentheses and probably put what's underneath the radical in parentheses as well. Now if you're using one of the older calculators, it'll give you the parentheses. So in this case here we got left parentheses 0.26 minus 0.25 close parentheses divided by, for the square root, second x squared, and then 0.25 times 0.75 divided by 550, and close parentheses, and then hit enter. Now the z value we rounded 2 decimal places, so this will be rounded to 0.54. So here, that test statistic from that sample data is going to be 0.54. Okay, so that's how we calculate a test statistic. In this case, it's for a proportion, so we have to use this formula. Example E5 is the same way. The claim is that the proportion of adults who smoke a cigarette in the past week is less than 0.35, and the sample statistics include N is equal to 1261, with 467 saying that they smoke a cigarette in the past week. Find the value of the test statistic. Okay, so in this case here, we're letting P equal to 0.35, which means Q is equal to 1 minus 0.35, or 0.65. Now in this case, we got N is equal to 1261, and X, where 467 said that they smoked a cigarette in the past week. So in this case, P hat, that's equal to X over N, which is 467 over 1261. And we'll leave this as a fraction. And you'll see why. Okay, so in this case here, we'll do Z is equal to P hat minus P divided by the square root of PQ over N. Okay, how did I know I had to use this formula? Because we're dealing with a proportion. So we use the formula for finding the test statistic of a proportion. Okay. So here, for a proportion, it's going to be that particular formula here. And then we just substitute those values into that formula. So in this case here, P hat is, let's say 467 over 1261 minus P, which is 0.35, divided by the square root of P, which is 0.35, times 0.65. All that's divided by N, which is 1261. Okay, so here's how we enter this in the calculator. Okay, we start with left parentheses, and then we'll do 467 divided by 1261 minus 0.35, and close the parentheses. And then that's divided by, and then second x squared for the square root, 0.35 times 0.65 divided by 1261, close parentheses. Hit enter. To two decimal places, that will be 1.51. The z values you always round to two decimal places, so it will be 1.51. So for the sample statistics that's given, our test statistic will be 1.51. Okay. Okay, now let's go back to our p-value method, which was the probability of getting the value of the test statistic that is at least as extreme as the one representing the sample data, assuming that your null hypothesis is true. And that was one method of interpreting that test statistic. The other method is the critical value method, sometimes called the traditional method. And of course, we need to define critical value. Now, we did talk about critical values when we were testing a claim, estimating a population proportion, estimating a population mean, and a population variance or standard deviation. The critical value is the value that separates what they call the critical region, or that shaded area that I talked about, from the values of the test statistic that do not lead to rejection of the null hypothesis. Okay, that critical value, that's going to be that boundary value that's going to separate the values of the test statistic that do not lead to rejection of the null hypothesis from the critical region. Okay, and I also have a handout with, it also has not only does it have the common phrases for hypothesis testing, it also has the common critical z values for hypothesis testing. Okay, so if you have a one-tail test, which is left tail or right tail, you'll look in this column and then read across to find out what your critical value is. And if you have a two-tail test, you'll look in this column here and then read across to find out what your critical z value is going to be. Okay, so in this particular, so here I have a couple of examples that are just like that. All right, let's start with this one. Let's say we want to assume that the significance level is alpha is equal to 0.01. Here you want to use the given information to find the p-value and the critical values. In this case here, you're told that the test statistic of z is 1.46, and that's obtained when testing the claim that p is greater than 0.09. Okay, so in this case here, if I draw a normal curve, let's say I want to draw the normal curve that looks like this. Alright, in this case here, p is greater than 0.09. Well, that greater than symbol tells me it is a right tail test. So we're going to be dealing with the shaded area that's on the right. And here, my test statistic is right here, 1.46. So I want to find that area that's to the right of 1.46. Okay? Now, in this case, if you recall, if you remember your standard normal distribution table, okay, so in this case here, let me go ahead and pull that out. It is for positive z-scores. There's one for negative, if you recall. And that z value is 1.46. Okay? Now, here's 1.4. And then 0.06 is over here. So if I read across and down, that number is 0.9279. However, it is a right tail test. That 0.9279 represents the area to the left. If you recall with table A-2, it's always the cumulative area from the left for your standard normal distribution table. You want the area that's on the right hand side. So what we're going to need to do here to get that p-value, we do 1 minus, and it's 1 because the area underneath the curve is 1. 1 minus that area that's on the left, which is 0.9279. So if you do 1 minus 0.9279, that would give you 0.0721. Oops. 0.0721. So this right here, that's shaded in red, is your p-value. Okay? That represents the probability of getting a test statistic that is extreme as the one that we've obtained from our sample data. 0.0721. Not only that, we also need what they call the critical value. Okay, now, this is where we use this table for the common critical z-values for hypothesis testing. Now, in this case, it is a left tail test, so we look under the column for level of significance in one tail. And that significance level that was given to us is 0.01, I'm sorry. 0.01 is your level of significance in one tail. Now, if we read off to the right, this is your critical value right here, 2.33. And it's a positive 2.33 because it is a right tail test. So the critical value would be 2.33. Now, had it been a left tail test, then it would be negative 2.33. Okay. All right, here's another example of finding p-values and critical values. Assume that the significance level is alpha is equal to 0.1. Use the given information to find the p-value and the critical values. Here your test statistic z is equal to negative 1.23, and that's obtained when testing the claim that p is less than 0.2. Well, let's take a look at that p is less than 0.2. That less than tells me it is a left tail test because it's less than. Points to the left, so that region that I'm talking about is going to be the area on the left-hand side. So it's this area on the left-hand side. That's the p-value that I'm trying to find. For z is equal to negative 1.23. And it is a negative z-score, so let's use the negative z-scores of our standard normal distribution and find negative 1.2. Well, negative 1.2 is right here, and 0.03 is this column right here. So negative 1.2 and down to 0.03, that will be 0.1093. 0.1093. And it is the area to the left that we're trying to find. That's this area right here to the left. That's what we're trying to find. So that p-value is simply 0.1093. Okay. Now we need the critical value. Okay, now critical value is negative because it is a left tail test. So the critical value is negative. And that's where we use this table right here. The common critical z-values for a hypothesis test. That alpha is 0.1 and it's in one tail, so we look under here for the level of significance in one tail, which is 0.10. Read that number off to the right. That critical value is 1.28. So in this case here, your critical value is z, that's equal to a negative 1.28. Why is it negative? Because it's a left tail test. Okay, another example would be this. Assume that the significance level is alpha is equal to 0.1. Use the given statement and find the p-value and the critical value. Here your test statistic of z is negative 1.26, and it's obtained when testing the claim that p is equal to 1/5. Well, that will have to be the null. The alternative will have to be the opposite of equal to, which is not equal to. Okay? P is not equal to 1/5. That's your alternative hypothesis. And based on that alternative hypothesis, not equal to means I have a two-tailed test. Okay? So it's going to be the area in two tails. Now when I find the p-value, since it's a two-tailed test, I have to take 2 times the area beyond the test statistic. 2 times the area beyond the test statistic, which is in this case, that z is negative 1.26. And it is a negative z value, so we find negative 1.2. We use our standard normal distribution table, find negative 1.2, and then 0.06 is this column here. Read across and down. It will be 0.1038. Okay? But that's only half your p-value. Okay? So to get the whole p-value, since it's a two-tailed test, you have to take 2 times that probability value. So it'll be 2 times 0.1038, which will be 0.2076. Okay? So your p-value there will be 0.2076. Okay? So now, anytime you have a two-tailed test and you're finding the p-value, it's always 2 times the area beyond that test statistic. Now for the critical values. And I say critical values because in a two-tailed test, instead of 1 critical value, you have 2 of them. One's positive and the other one is negative. Okay. Now this time, using our common critical z-values for hypothesis testing, we're going to be looking under this column for the level of significance in two tails. And we're going to be using 0.10. That's given to us because that's the level of significance and it's in two tails. Look to the right, you'll see your critical value is 1.645. Now, however, it's a two-tailed test, so that means we have 2 critical values. One will be a negative 1.645. The other one will be a positive 1.645. Okay. Okay, now the next thing I need to cover is steps 7 and 8 on your procedure for hypothesis testing. And step 7 is just simply stating whether to reject the null or fail to reject the null hypothesis. Okay, so here you're going to be making a decision. Okay. So your decision rule is going to be this. You're either going to reject the null, because you're always testing the null to see whether or not you need to reject the null or fail to reject the null. Okay. And that's based on which method that we use, either the critical value method or the p-value method. Okay, now, if we were to use the p-value method, we compare the level of significance with our p-value. And if that p-value is less than or equal to alpha, then you reject the null. Or if the p-value is greater than your alpha level of significance, you fail to reject the null hypothesis. And then for the critical value method, you'll compare your test statistic with your critical value based on alpha and the type of test that you have, whether it's a left tail, right tail, or two-tail test. If that test statistic is in the critical region or the shaded critical region, you reject the null. or if the test statistic is not in that critical region, you're going to fail to reject the null hypothesis. Okay? That's very important because you're going to have to pretty much make that decision on whether to fail to reject the null or reject the null based on some information that's given to you. The p-value method, you have to compare your significance level with the p-value. The critical value method, you compare your test statistic with that critical value. Okay, and then the final step, which is step number 8, that's restating the decision using simple, non-technical terms. Okay, and also on your handout with your hypothesis testing procedure, this will help you in wording the final conclusion. Okay, so here the claim could be either the null hypothesis or the claim could be the alternative hypothesis. Now, if the claim is the null and you reject the null, then you'll start this statement by saying there is sufficient evidence to reject the claim. Now, if the claim is the null and you fail to reject the null, then you'll start by saying that there is not sufficient evidence to reject the claim. Now, if your claim is the alternative hypothesis and you reject that null, then you'll start by saying that there is sufficient evidence to support the claim. Or, if the claim is your alternative hypothesis and you fail to reject the null, then there is not sufficient evidence to support the claim. Okay, so you'll be using this part right here to assist you in wording the final conclusion. And that's step number 8. Okay, now let's look at some examples of just that. Okay, in this case here, let's start by assuming that the significance level is 0.05, and we use the given information to complete parts A and B below. Here the original claim is that the proportion of male golfers is more than 0.2. The hypothesis test result in a p-value of 0.012. Here you want to state the conclusion about the null hypothesis, whether to reject the null or fail to reject the null hypothesis. And without using technical terms, this is part B, state the final conclusion that addresses the original claim. Now, if you want to, you can do this. State your null and your alternative hypothesis. Here, the proportion of male golfers is more than 0.2. Well, more than is greater than 0.2. And it's strictly greater than, so that's your alternative hypothesis, which means the null has to be p is equal to 0.2. Okay? Now, part A, we're given a p-value. So let's compare the p-value with our level of significance. That rule is this: if your p-value is less than or equal to alpha, you reject the null. And in this case, the p-value was 0.012, your alpha level was 0.05. And by comparing those two, 0.012 is less than 0.05. So that satisfies our decision rule, so that means we reject the null hypothesis. Okay. Now part B is stating the final conclusion that addresses the original claim without using technical terms. Well, here, your alternative hypothesis is the claim, because you're told that the proportion of male golfers is more than 0.2. So going back to this, our claim was the alternative. We already rejected the null. So that means we start that sentence off by saying that there is sufficient evidence to support the claim. And then we finish the rest of the sentence. Okay? That means that there is sufficient evidence to support the claim that the proportion of male golfers is more than 0.2. Okay. Now, if you was taking a face-to-face statistics class, you would be required to write all of that. And that's very important. Okay. Alright, now let's look at this next. This kit contains a lot of parts in this particular problem. A 0.05 significance level is used for a hypothesis test that of the claim that when parents use a particular method of gender selection, the proportion of baby girls is different from 0.5. Assume that the sample data consists of 91 girls and 169 births, so the sample statistic of 7 over 13 results in a z-score that is one standard deviation above 0. Okay? And then you're going to complete parts A through H below. In this case here, you want to identify the null and the alternative hypothesis. Okay, so we'll do each one of these one at a time. So in this case, it will start with part A. And in this case here, we want to state the original claim. Okay. Okay, starting with the original claim, where the proportion of baby girls is different from 0.5. Your proportion is going to be lowercase p, and that's different means not equal to 0.5. Okay? So if you look at your hypothesis test for common phrases, you'll see is different from means not equal to when you write it in symbolic form. So the original claim is p is not equal to 0.5. The opposite is this. If it's not equal to 0.5, then the proportion must be equal to 0.5. And then write your null and your alternative hypothesis. One of these will be the null, the other one will be the alternative. And the alternative always does not have equality in it. It's either got the less than or the greater than or not equal to. In this case, that's your original claim. P is not equal to 0.5. The null always has equality in it. It always has the equal sign no matter what. And by the way, your alternative hypothesis is your claim, because that's what the original claim is. It says that right there. So that's part A, stating the null and the alternative hypothesis. Part B, what is the value of alpha? Well, right off the top we see 0.05 significance level, so that's your alpha level, 0.05. Part C, what is the sampling distribution of the sample statistic? In this case here, we're dealing with a normal distribution, because we're testing a claim about a proportion in this case. So with a proportion, it's a normal distribution. So in this case, that sampling distribution would be a normal distribution. Part D. Is the test two-tailed, left-tailed, or right-tailed. Well, let's look at our alternative hypothesis. We have a not equal to symbol here, so that tells me it is a two-tailed test. This is a two-tailed test. And then part E, what is the value of the test statistic? Well, in this case here, normally you would use the formula. However, if you take a look at this, the sample statistic of 713 results in a z-score that is one standard deviation above 0. So z in this case is 1. And I'm going to say 1.00. Okay, because as you can see, that's already given to us in the problem. Now, if it didn't say that, then you'll have to use that formula to calculate your test statistic. That's z is equal to p hat minus p, all divided by the square root of p times q divided by n. Alright, now part F, what is the p-value? Okay, so here's how we find the p-value. Here's 0, and here's 1. Now, it says a left-tailed test. So that means, not equal to means it's a two-tailed test. It is a two-tailed test. So the p-value is going to be 2 times the area beyond that test statistic. Okay, so when we use table A-2, or the standard normal distribution table, it's not negative z-score, it's a positive z-score. We have to take 2 times that area to the left, beyond that test statistic. In this case here, we find 1.0 and then 0.00, read across and down, that's going to be 0.8413. But keep in mind, 0.8413 is that area to the left. We want the area to the right. Okay, and I don't want to say p-value yet. So the area to the right is going to be 1 minus 0.8413, which will be, in this case, 0.1587. And then we can find the p-value. So that p-value, that's this area right here that we're trying to find, would be 2 times 0.1587. And that's going to give me 0.3174. So that p-value is going to be 0.3174. That represents the probability of getting a test statistic as extreme as the one that we've obtained from our sample data. Okay, so that's part F. Part G, they want the critical value. Actually, yeah, 2 critical values since it's a two-tailed test. Okay. Now, in this case, we're dealing with a 0.05 level of significance in 2 tails. So we look at level of significance in 2 tails, find 0.05, read the critical value to the right, that's 1.96. And since it's a two-tailed test, we have 2 critical values. One will be z is equal to negative 1.96, and z is equal to positive 1.96. Okay. Now part H is what is the area in the critical region. Well, the area in the critical region is your alpha level. That's 0.05. So here, if we were dealing with these critical regions right here, that's 0.025. That's 0.025. Put them together, you'll get 0.05. Okay. Okay, there's one last thing I need to cover that is going to be very important. Well, actually, there's a couple more things I need to cover. Starting with this one, the fact of accepting the null versus fail to reject. If you use the word accept, that's misleading because it implies incorrectly that the null hypothesis has been proved. Now keep in mind, we can never prove a null hypothesis. Okay? Now, when we test a null hypothesis, we never, and if we end up failing to reject the null hypothesis, we haven't proved anything. We haven't proved that the null hypothesis is true. We're just saying that we just failed to reject the null, which is more of a correct way of saying that, because that's stating that there is available evidence that's not strong enough for us to reject the null hypothesis. Okay? So we can never accept a null hypothesis, and we can never prove a null hypothesis. Okay? So it's better to say fail to reject the null hypothesis as over saying accept the null. Alright, now there are two types of errors in hypothesis tests. So I need to go ahead and go over those, and then I'll cover that last example for this video. And there are two errors in hypothesis testing that we can commit. One of them is a type 1 error. And a type 1 error is the mistake of rejecting the null hypothesis when it is actually true. Okay? The mistake of rejecting the null hypothesis when it is actually true is committing a type 1 error. And then the second type of error is a type 2 error. And the type 2 error is the mistake of failing to reject the null hypothesis, which is H sub 0, when it is actually false. Okay? The mistake of failing to reject the null hypothesis when it is actually false is committing a type 2 error. So in this case, now you're always testing the null hypothesis regardless to determine whether it is true or false. So H, the null hypothesis could be true, or the null hypothesis can be false. Because everything in this case is just going to be based on the null hypothesis. And then your decision is either to reject the null or fail to reject the null. Okay. If you reject the null hypothesis, that means if you reject that null hypothesis, you cross it out, but it is true. that null hypothesis is true, and then you reject the null hypothesis, then that is a type 1 error that you have committed, as you have rejected a true null hypothesis. You reject the null hypothesis, you throw it out, and that null hypothesis is false. That's the correct decision. Okay. Let's say you fail to reject the null hypothesis, and it is true. That means you don't throw out that null hypothesis, and that null hypothesis is actually true. That's what you want. That's the correct decision to do. Now, if you fail to reject the null hypothesis, you fail to throw it out, but that null hypothesis is false, then you've committed a type 2 error. Okay. Now, let's look at something that is probably real life, like a court case or a criminal case. Let's say, for example, a person is already on trial. Let's say Alex is on trial, and the null hypothesis is this: Alex is innocent. That means he didn't commit that crime. That's your null hypothesis. The alternative hypothesis in this case would be this: Alex is not innocent. Okay. Now again, we're testing the null hypothesis to see if it's true or false. So either the null is going to be true, that means that Alex is innocent, or the null hypothesis is false, meaning that Alex is not innocent. And usually in court cases, in criminal cases, when a jury reaches their verdict, their verdict is based on what was presented to them in court. And that's based on the evidence that's presented in court. So here, you could reject the null or fail to reject the null. That means you could reject his innocence or fail to reject his innocence. So this is fail to reject the null hypothesis. That's his innocence. Okay? You reject the null hypothesis, you reject his innocence. But it is true that he is innocent. That means you rejected a true null hypothesis. That is a type 1 error. Okay? Let's say you reject Alex's innocence, and he is not innocent. He is guilty. That's the correct decision. Okay. Okay. So here you rejected his innocence, and it is true. That means that you sent an innocent person to prison. Now, if we fail to reject the null hypothesis, and that null hypothesis is true, we fail to reject his innocence, that he is innocent, and it is true that he is innocent, that's the correct decision. But let's say that we fail to reject his innocence, and we find out that he is not innocent of the crime, then that's a type 2 error. In other words, we let someone who probably committed that crime go scot-free. Okay? So this is just a real-life example of a type 1 and a type 2 error. Okay, now let's look at this last example that deals with type 1 and type 2 errors. Here you want to identify the type 1 and type 2 error that corresponds to the given hypothesis. The percentage of adults who have a job is greater than 88%. Alright, in this case here, let's start with this original claim. that original claim is this. The percentage of adults who use P is greater than 0.88. And then our opposite, if it's not greater than, that means it's less than or equal to 0.88. And then from that, we can write our null and alternative hypothesis. Okay, the one that has strictly greater than is our alternative hypothesis. The null always has the equal sign, so P is equal to 0.88. And that alternative here is the claim, because the original claim says P is greater than 0.88. Okay, now let's use that, create this table that will help us determine the type 1 and type 2 error. The null is either going to be true or the null is going to be false, because you're always going to test the null to see if it's either true or false. And you're going to use the null to either reject the null or fail to reject the null. Okay, we're rejecting the claim. No, we're rejecting the null. We're rejecting the fact that the proportion or the percentage of adults who have a job is 88%. And it is true. That's a type 1 error, because we have rejected a null hypothesis when that null hypothesis is true. And then for this one, if we reject the null and the null is false, that's the correct decision. Because you do want to reject something that is false. Now, if your null hypothesis is true and you fail to reject the null, that's what you want. The correct decision. And if we fail to reject the null, but that null is actually false, then that's a type 2 error, by definition. So from this, my type 1 error is this. You're rejecting that the percentage of adults who have a job is equal to 88%, because the null hypothesis says P is equal to 0.88, so it'll be 88% when it is actually 88%. That's the type 1 error. Now from the type 2 error, we're failing to reject the fact that the percentage of adults who have a job is equal to 88% when it is actually, in this case, the alternative, greater than 88%. So here's our type 2 error in a statement. And that's failing to reject that the percentage of adults who have a job is equal to 88%, when in fact the percentage is greater than 88%. Okay, so that's how we write that as a sentence for the type 1 and the type 2 error. Okay. Okay, now I realize that that is an awful lot in this particular video to explain, but here it is very important because this is going to be setting the setting up the things that we're going to be talking about when we test a claim about a population proportion, a population mean, and a population variance or standard deviation. And that will conclude this particular video on the basic concepts of hypothesis testing.